Welcome to projectile motion. So far we've looked at motion in one dimension, whereas if I drop this red object, it would fall at 9.8 meters per second squared. If I knew its initial velocity, which is 0 in this case, I could tell you how fast it's moving at any point in time. Or if I gave you a velocity, you could tell me how long it would take until it got to that velocity with the equations of motion. But what projectile motion introduces is it introduces an x velocity as well. It's no longer an object just falling, but the object has a velocity in the x direction. The main thing to consider here is that both objects are accelerating downward at the same rate. That is 9.8 meters per second squared. And if you look at them, you'll see that. But the object has a constant velocity in the x direction. That is, its change in position versus time in the x direction is constant. That is the main objective behind projectile motion, is to understand how that works. Now if we look at this scenario, we have an object that's launched at some initial velocity at an initial angle. What we're going to do in every single one of these problems is find the initial velocity in the y direction and the initial velocity in the x direction. And we're going to do that because we know the hypotenuse and the angle. And v0 y will be the opposite side and v0 x will be the adjacent side. So I'll go over that in a moment. What you'll see here is as the object, the ball in this case, is launched upwards, Vx is continuously the same. That is, there's no acceleration in the x direction. But in the y direction, the acceleration is negative 9.8 meters per second squared. So velocity is in the positive direction, and it gets lower and lower until at the highest point in the trajectory, the motion of the ball is called a trajectory. At its highest point, the velocity is 0. And then the velocity keeps getting more and more negative. So when it lands, or when it ends up at the exact same height that it was launched, its final velocity will be exactly equal but opposite in direction. And that is actually going to be the case at each of these heights as well. We'll learn when we do the equations of motion why that works exactly. Speaking of the equations of motion, this is the same thing. V0 is at a lower angle, so we can find V0 x and V0 y. And you'll see that V0 x is constant. And in the y direction, you're basically having an object that's thrown up in the air and then comes back down. And in the x direction, it's moving along at a constant velocity. So we need to divide up our velocities into the x and y direction, and we need to look at different equations in both directions. Now, our x equations in this case, Vx is going to equal V0 cosine theta. And that is because x is adjacent, the adjacent side to the angle. So Vx equals V0 cosine theta. And any point in the x direction is just V0 cosine theta, the velocity in the x direction, times time. Now, v in the y direction is V0 sine theta. So, v initial in the y direction V0 y will simply equal V0 times sine theta. But as the object moves through time, the velocity is going to change, so we'll get v equals V0 minus at. Or the original equation of motion for that is simply V final equals V initial plus AT. So you're seeing that equation right here. And then if we look at V final equals V initial, D final equals D initial, which is 0, plus V naught T plus 1/2 AT squared. This is the equation for the object at any point in time. Alright, when we continue, what we're going to do